All right, everybody, welcome back. Today we're going to study polynomial inequalities and rational inequalities. These are inequalities where one side of the inequality is a polynomial function or a rational function. So they both kind of follow the same pattern, but we get a little bit of extra mileage with polynomials because we are quicker at drawing a picture there. So the general steps are as follows. Well, first, if we have a polynomial on both sides of our inequality, we'll just rearrange everything so that we just have 0 on one side. That'll make this a little bit easier to start with. Then we'll take the polynomial we have on the other side and set it equal to 0. Because ultimately, we'll have our inequality of the form polynomial is less than 0 or polynomial is greater than 0. So we'll first determine where it's equal to 0, and then everywhere else will be either one or the other of greater than 0 or less than 0. So once we solve our equation, set our polynomial equal to 0, and solve that is find the roots or the zeros of the polynomial in question. Then we'll create a little chart where we break up the number line according to the zeros of that polynomial, and then we get a whole bunch of little subintervals that break up the number line completely. And then in each one of those subintervals, we'll just pick our favorite point that we like, our favorite x value, and just evaluate the polynomial in question there and see if what we get is bigger than 0 or less than 0. And if our test point is, say, bigger than 0, then the polynomial is bigger than 0 all over that interval. And similarly, if our test point evaluates something negative, then that polynomial is negative all throughout that subinterval. Okay, so let's get started here. We'll have x squared minus 6x plus 8 is less than 0. So this one's already, step 1 is already done for us here. So we'll take the polynomial in question, x squared minus 6x plus 8, and set it equal to 0. And I believe that it factors as x minus 4 times x minus 2, since minus 4 and minus 2 are two numbers whose product is 8, but whose sum is minus 6. So then the two zeros for this polynomial are x equals 4 or x equals to 2. Okay. So now we'll break the number line here into 3 subintervals separated by these points x equals 2 and x equals 4. And we'll test our favorite x value in each one of these subintervals. So now for the subinterval that is less than 2, my favorite x value is 0. It's easy to evaluate things at 0, right? And so we'll evaluate x squared minus 6x plus 8 at x equals to 0, and we get 8, which is positive. So I'll mark that with a plus sign to denote that this polynomial is positive on this whole interval. Next is the interval between x equals 2 and x equals 4. My favorite x value there is x equals 3. And we can evaluate our polynomial there. I'd say I kind of prefer to evaluate the factored version. It's typically, sometimes it's quicker. If all you care about is positive or negative at the end, then you can just see how many negative numbers you have in your product. If you have an odd number of negative numbers, your product is negative. If you have an even number of negatives in the product, you have a positive. Okay, so here we get 3 minus 4 times 3 minus 2. That's minus 1 times 1, so that is a negative number. So in fact, the polynomial in question is negative all throughout this subinterval. Okay, last but not least, we have the interval of numbers that are bigger than 4. My favorite one to test there is x equals to 5, where again, I'll evaluate the factored version of the polynomial. So we get 5 minus 4 times 5 minus 2. Those are both positive numbers, so the product is also positive. Therefore, this polynomial is positive all throughout this interval. Okay, so then the question asks us to find when is this polynomial less than 0? Well, the only time we found was in this interval between 2 and 4. And it's asking us for strictly less than 0, so no equals to here. So we will have just the open interval from 2 to 4 like this. Now notice that this question, we could graph this parabola, right? X squared minus 6x plus 8 is graph is a parabola. And we can see that graph here, right? And it looks like from the graph here that the only x values for which the corresponding y values are negative are the x values between 2 and 4, right? It is y values are positive everywhere else. So that's another way you might go about answering a question like this if you're able to graph the polynomial in question. All right, so let's move on to the next one. They give us 3x cubed minus 4x squared is bigger than or equal to 75x minus 100. So the first thing we want to do is get 0 on one side. So I'm going to subtract 75x from both sides, and I'm going to add 100 to both sides to give me 3x cubed minus 4x squared minus 75x plus 100 on the left. And we want to know, when is that bigger than or equal to 0? So I believe we can factor the left side here by grouping. So in the first pair of terms, the common factor is x squared, which will factor out, and we have 3x minus 4 left over. And in the second pair of terms, minus 25 is common to both, and we can factor that out, and what we're left with is again 3x minus 4. So in our step of setting this polynomial equal to 0 and solving, we can solve by using factoring, where we do this factor by grouping. So then now we have a common factor of 3x minus 4. It's common to both ones, so we can pull it out. And what's left over when we factor it out? Well, we have x squared on the first term and minus 25 on the second one. So this whole thing now factors as x squared minus 25 equals to 3x minus 4. Or sorry, x squared minus 25 times 3x minus 4. Sorry, I'm losing my mind. And then we want to set that one equal to 0 to see when is this polynomial equal to 0. So either x squared minus 25 is 0, or 3x minus 4 is 0. So in the first case, we get x squared is 25, which gives us x is plus or minus 5. And in the second case, we get 3x equals to 4, which means that x is 4/3. So now we have 3 zeros for this polynomial in question. So we're going to get a few more subintervals this time. But that's fine. So our smallest one is minus 5. Our second one is 4/3. And our third one is 5. So, oh gosh, so now we have 4 intervals to check. So in the first one, the set of x that are less than minus 5, I'm going to test x equals to minus 6. And again, I'm going to evaluate the factored version. I could have maybe even factored it a little bit more. X squared minus 25 is a difference of squares, so it factors as x plus 5 times x minus 5. But that's fine. We don't need to go all the way. We'll just keep it like that. So if we do minus 6 squared is 36, and then subtract 25, that gives us a positive number. And 3 times minus 6 minus 4 gives us a negative number. And so a positive times a negative is negative. So the polynomial in question is negative all along this subinterval for x less than negative 5. OK, the next one to check is the interval between negative 5 and 4/3. My favorite number in between there is x equals to 0, because it's very easy to evaluate things at 0, right? So what do we get? 0 squared minus 25, that is a negative number. And 3 times 0 minus 4, that is also a negative number. So the product of these two negative numbers is positive. So in fact, then the polynomial is positive all in the subinterval between minus 5 and 4/3. OK. Next on the list is the interval between 4/3 and 5. And my favorite number in between 4/3 and 5 is x equals to 2. And so we can evaluate our factored polynomial there. We have 2 squared minus 25. That's a negative number. And 3 times 2 minus 4 is a positive number. So that product is negative. And therefore, the polynomial is negative all throughout this subinterval from 4/3 to 5. OK, and now last but not least, we have the interval from 5 to infinity. And so my favorite x value in between there is x equals to 6. And we can evaluate that 6 squared minus 25 times 3 times 6 minus 4 is a product of two positive numbers and is therefore positive. It follows then that the polynomial in question is positive all throughout this interval from 5 to infinity. And so we found the places where this polynomial in question, 3x cubed minus 4x squared minus 75x plus 100, is bigger than 0 and where it's equal to 0. So we can answer with some closed intervals now because we have that greater than or equals to sign in our in the directive here. So we get the interval from -5 to 4/3, including the endpoints, union with the interval from 5 to infinity, including 5. Okay, and once again, this one we could have done maybe graphically if we know the end behavior of this cubic polynomial and we know all of its zeros, then, and their multiplicities, I guess, as well. They all have multiplicity 1, I think. So we can also do a graph of this polynomial and see that the intervals in question from -5 to 4/3 and from 5 to infinity are exactly the places where this polynomial's y values are positive or 0. Okay, so that might be enough for now. This next example is a little bit more involved. But what happens? The first thing that we do is subtract everything, and we get 0 on the left side now. And on the right side, we have a 5th degree polynomial, x to the 5th minus 11x to the 4th plus 32x cubed minus 28x squared. And there is a hint here. The hint says that x equals to 2 is a 0 of this polynomial. So that's not obvious to me. So I guess we're going to have to use that information and get some more information out of it. So let's see. So the first thing I know I can do is that there's a common factor of x squared to all of this. So I'll factor that out, and I'm left with x cubed minus 11x squared plus 32x minus 28. Now really, x equals 2 is not a 0 of x squared, so it must be a 0 of this cubic polynomial that's left over here. But if you remember from the lecture on the Friday right before our extended spring break, we learned that if x equals to 2 is a 0 of this polynomial, then the polynomial x minus 2 is going to be a factor of this cubic polynomial. In other words, we can do polynomial division of x cubed minus 11x squared plus 32x minus 28 divided by x minus 2. And what we'll get is a quotient with 0 remainder. And so I've shown that work off to the side here. I don't know if I want to explain all of it right now. I think it's pretty evident if you know how this works. If you have questions about that, we can talk during class, or you can email to me. And so what we get then is that when we divide out by x minus 2, we're left with x cubed minus 11x squared plus 32x minus 28 equals to x minus 2 times x squared minus 9x plus 14. So I will replace x cubed minus 11x squared plus 32x minus 28 over here with this factored expression here. And oh, we know how to factor the remainder term here, this x squared minus 9x plus 14. Two numbers whose product is 14 but whose sum is minus 9 are minus 2 and minus 7. So we can factor the total 5th degree polynomial we started with as x squared times x minus 2 times x minus 2 times x minus 7. Notice that we could really simplify that to x squared times x minus 2 squared times x minus 7. So in fact, we get 3 zeros, x equals to 0, x equals to 2, and x equals to 7. And it looks like for the first 2 zeros, they have multiplicity 2. The last 0 has multiplicity 1. That might help us out if we're doing some kind of graphical solution. But if we don't want to do the graphical solution, then we'll just go for it and test points like we had before. If we test all the values, or we can test a value that is less than 0, my favorite one is -1. And if you look there, you can evaluate this factored polynomial. I like the factored one better here. And get something which is negative. My favorite x value between 0 and 2 is going to be x equals 1. And when we evaluate our factored polynomial there, we get another thing that is less than 0. So the polynomial in question now is less than 0 on both of these two intervals. Oh my gosh, for the interval between 2 and 7, we have, let's test x equals 3, and we can evaluate our factored polynomial and get something negative yet again. And okay, in the last possible case here, I'll test x equals 8. That's a number that's bigger than 7. And I finally get something that is actually bigger than 0. And so we were tasked with finding what intervals this polynomial, this 5th degree polynomial, is bigger than 0 on. And it turns out it is just this last one here, the interval from 7 to infinity. And so let's see, the next one here, there's one about cattle on a South Texas ranch. I've set up for you here, and you can knock it down for a bonus homework if you like. But when we come back, we'll meet rational inequalities and play this same exact game with not polynomials, but rather rational functions instead.